when you say no loops, what are you saying by no loops?
I want every element to be able to appear in basis.
Right. Okay. And when you're talking about the rank, you're talking about the number of basis elements.
Yes.
So I'll remind you that we were talking about circuits. We were talking about circuits of a matroid, and we said that maybe it was worthwhile to study not just independence, but dependence. We said that circuits would do that for us. And the last thing we did last time was come up with some good properties of circuits. Which we call C1, C2, and C3. C1 was this triviality, non-triviality property that the empty set better not be a circuit. Condition 2 told us how to go from a bigger set to a smaller set. So it said if C and D are circuits, no, sorry, if C is inside D and not equal to it, and D is a circuit, then C cannot be a circuit. Okay. And we expected these to be the two kind of easier axioms, and this one to be the interesting one is how do you build a third circuit from two of them? So we said if C and D are circuits and they intersect, say we call the element E is in their intersection, then basically I can use the two circuits to eliminate E and find a third circuit. Then I can find a third circuit, let's call it E, which is inside the union and does not use this element E. Okay. So last time we proposed these three as three good characteristics of circuits. And the question that we left open was, are these good axioms or not? And what we mean is, do these characterize the matroid? Is this an equivalent definition of a matroid or not? And the point is that it is. That's our theorem.
So we're using E both to be the ground set and
Thank you. Never let me call a set E, because E is usually denoting the ground set, so I shouldn't be calling this guy E. Let me call it F. I wanted to call it B, but then B is usually denotes a basis. So, okay. Proof. So I need to do two things. I need to show that if I have a matroid in our independence definition, then it satisfies these axioms, and that if I have these axioms, then I have the independence axioms also. So let's go first in the forward direction and say, suppose that you do have a matroid. And suppose that we have it in terms of independent sets. And let C be the set, the collection of circuits. So we need to show that this satisfies the three axioms. The empty set is not a circuit. Why? Because axiom number 1 says the empty set is independent Actually, before I say this, let me explicitly remind you that the collection of circuits is basically the minimal dependent sets. Minimal. I should also tell you that I'm going to do it very often. People often do this. M-I-N-L is short for minimal. Minimal sets which are not independent. So minimal sets not in I. So the first axiom that I need to check is clear, because the empty set is independent. It's not a circuit. Second axiom, suppose C is inside D and D is a circuit. We want to conclude that C is not a circuit. Well, if you suppose that C is a circuit, to get a contradiction, the contradiction is right there, because D is supposed to be minimal. And now you find a C inside it that is also a circuit. This contradicts the minimality of C, of D. So as usual, the first two axioms are very easy. And the work here is the third axiom. So suppose that we have C and D, which are circuits, and let E be in the intersection. And suppose that there's no circuit. Suppose no circuit in C union D minus E. If there is no circuit in there, that must mean that C union D minus E is independent. Because if it was dependent, then it will contain a minimal dependent set, which is a circuit. Okay. So here I have an independent set. Okay. Now, how do I build a proof here? What I want to do is use the independence axioms to say something about circuits. So far, I have one independent set in my picture, this C union D minus E, and I need to find other independent sets that I can play with to use the axioms. Now, C and D are dependent, so I cannot use them. But how can I get an independent set here? Well, one thing I can say is, let me take C and remove something from it. If C is a circuit, then when I remove something from it, that's independent, and that's something I can actually play with. So let me take an element, and let me see what I called it in my notes. I had called it Y, but I had also called E X. So to be consistent, let me take F be in C minus D. The point being that if F is in C, then C minus F is independent. So I want to take F in C, and you will see in a second why I want it not to be in D. But if these two guys are different, then I can find an element that is in one and not in the other. Okay. C minus F is independent. And so now here I have two independent sets, and I can actually do something with the axioms. Okay. I can say, well, this guy is smaller than this guy, right? They're both independent. And that means that because they're both independent, I can take an element from this guy and expand this guy. So I can take C union A minus F independent, where A comes from this side over here. Okay. But if A comes from this side, then it can't come from C, it must come from D. So if I add something to C here, then I'm not expanding this guy at all. Yeah?
Why is that strictly less than? How do we know that C and D are the same, sort of the same set?
How do I know that this is strict?
Exactly. Yeah.
How many elements does this guy have? It has the number of elements in C minus 1. Now, this guy has the number of elements in C minus 1, plus some things that I might add from D.
Right.
Now, the question is, how do I know that I actually am adding something from D?
Right. I know that D isn't strict. Oh.
Well, F is
oh,
in
right.
C minus D.
Right.
You're assuming that.
D can't be a subset of
D
C because C is minimal.
Right, I mean, exactly. So the point is that D cannot be a subset of C, so there must be things in D.
Right.
And if there are things in D, then those are not in here. If there are things in D that are not in C, then those are not in here. Okay? So I add something from D. Okay? Now, two things might happen, that they're equal or that there are other things. So if let me first assume that I added A and this guy is still smaller. Okay? Then if this guy is still smaller, then I can add another one. And the point is that as long as this guy is smaller than this one, I can keep adding things to it until I get the same size. So the point is exactly that I want to get to Chris's situation where actually these two are the same size. And I'm going to keep doing that until these two guys are the same size. But when am I going to get to a situation where these two are the same size? I keep adding things to this guy. How can these two be of the same size if I keep adding things from D in here? Well, basically, when I'm done adding everything that was in D that was not in C, that's when this process is going to stop. Until I'm here. So something that you can always do. If you take a small independent set and a bigger one, then you can keep adding things from this one into this one until they're the same size. Okay. And in this case, I can only be the same size when I've added everything that was in D and not in C. Okay. And what I've concluded is that C union D minus F is independent. Now, I'm claiming that I have reached a contradiction here. Does anybody see that contradiction? The thing is, look at C union D minus F. This contains all the elements in D, except possibly F. But F is in C. So all the elements of D that are not F are contained in here. Okay. Actually, F is not even in D, so I don't need to worry about that. So
Right.
this guy is a subset of this one, but you see this guy is independent. I just proved it, and this guy is dependent, and that can't be. I can't have a subset of an independent set be dependent. That's my contradiction. That's my contradiction, and that proves C1, C2, C3. Okay. Now, I wanna make a point here, which is that I really honestly feel that these proofs are often easier to do them yourself than to watch someone else do them. And you might be watching me do this and say, okay, but why is he doing this at this step? Why is he doing it at this step? And very often what's going to happen to you is that maybe you can follow each step that I'm doing, but if you really want to understand what I'm doing, I can tell you a little bit about the motivation, but there's nothing like trying to do it yourself. Okay? And this is actually what I'm going to ask you to do for the other direction. It's good practice. So what you're going to do is show that if you have C1, C2, and C3, then you can basically more or less reverse this argument and get a matroid. So if C satisfies C1, C2, and C3, then you're going to define I. How would you define I? How do you define independent sets in terms of circuits?
Anything that doesn't contain a circuit.
The dependent sets are the things that contain a circuit.
Right.
The independent things are the ones that do not contain a circuit. So if you had a collection C that you want to show is circuits, then you want to define a collection I of things that sets not containing sets in C. Okay. You're trying to prove that C is the collection of circuits of a matroid. So these would be the independent sets of the matroid you're trying to find. Okay. And so what you have to do is, using this definition, using this definition and using these three axioms, you're going to have to prove the three axioms of independence. Prove I1 up to I3. Okay. This takes a little bit of work, but it's good exercise if you guys do it yourselves. So I leave it as an exercise. And if you get stuck, you can look up the proof, which is in Oxley's book.
Now, what are I1, I2, and I3 again? Those are the axioms for what?
These were the axioms for the independent sets of a matroid, which said, the first one was saying the empty set is independent. The second one was saying subsets of independent sets are independent. And the third one was this independence exchange axiom. So you would have to basically look them up and prove them.
So that's the same as C1, C2, and C3.
And the point when it comes to it is that these are equivalent axiom systems. So the axioms don't say exactly the same thing, but the point is that they are equivalent in the way that if you define an object satisfying these axioms, then what you have defined is a matroid. And if you define a structure that satisfies the independence axioms, then you have also defined a matroid. So this is a third way of thinking of a matroid. The first one was something that satisfies independence axioms. The second one is something that satisfies the basis axioms. And the third way is something that satisfies the circuit axioms. So there are three ways of thinking about matroids. Okay, but now the next point that I want to make is that these are definitely not isolated ways of thinking about matroids. And if you
What do you mean?
So what I mean by this is that whenever anybody's trying to prove theorems in matroid theory, they don't just say, okay, let me only use the independence axioms. The point is that you have all these different families of things you can use. So you can say, well, I know the independent sets satisfy this, so I'll use that. Then I know that the circuit satisfies this, so I'll use that. And in matroid theory, you know, logically these things are equivalent, but sometimes it's easier to use independent sets, sometimes it's easier to use dependent sets, and so on. And we're going to see an example now of a statement that is only about basis, but that if you want to prove it, you really want to use circuits. So the point is that these different points of view the independent set point of view, the basis points of view, circuits point of view, and we're going to see many other ones actually. are not isolated, you want to use them together. All simultaneously. And if you look further in the book, you're going to see that basically every proof has some parts that talk about circuits, some parts that talk about independent sets, etc. Okay. So here's a theorem. Which in my mind is one of the most amazing and fundamental theorems in matroid theory. And it says this. Let's say that you have a matroid. And let's say that you define it in terms of the bases. Okay. I'm going to write the theorem here, but I want you guys to have an example in mind. So let's go back to the same example that we keep talking about. So E is A, B, C, D, E, F. And the bases are, written this down so many times that I even memorized what the bases are. And what the graph looks like. You saw that this is this is a matroid independent of the fact that it comes from a graph, but it happens to come from a graph, and so it's useful to think of it this way. So we said this is A, this is B, this is C, this is D, this is E, and this is F. Okay. Now what you're going to do is define a new collection, B star. And in this collection, you're going to put the complements of the bases. Okay. So for each basis B, you're going to consider the complement, E minus B. Okay. So let's do that for this example. For each basis here, you're going to get a basis here. Okay. Here's a basis, A, B, C. So the complement is D, E, F. The complement of A, B, D is C, E, F. The complement of A, B, E is C, D, F. The complement of A, C, D is B, E, F. And the complement of A, C, E is D, D, F. Is it clear what I did there? Theorem. This is a matroid also. So these are also the bases of some other matroid. Which you can think of this in what it means is that this collection satisfies the matroid axioms. Okay. If I wanted to illustrate to you that this is a matroid, well, I could either do it by hand and show that for any two bases, if I take an element out of one, I can replace it with an element of the other one. But if I'm lucky enough, maybe this is a matroid that I already know. For example, if I'm lucky enough, this might be a graphical matroid or a transversal matroid or something like this.
I mean, just for this.
In this specific case.
Right.
So, for example,
It looks like that one. Right.
if you stare at this long enough, well, let me do it a little bit more slowly. So I think you guys are already far ahead of me. But the first thing I want to say is that if you work at it a little bit, you can find a graph that has these bases. Okay, actually, you can find several, but I'll draw one for you.
Federico, is that always going to be true if you have them, if your original matroid for this theorem is graphical, that your M star matroid will also be graphical?
That's an excellent question. So First, let me show you that it's true in this case, that if I started with a graph in this case, I'm lucky enough that this guy is also graphical. How do I do that? I'm just going to show you the graph. Okay. I'm going to call this F, A, B. To be a little bit suggestive, let me call this one B, this one C, and D, E. What are the bases of this matroid? Well, they all have to have F. They all have F. And then what else can you do? You can never use A, so you'd never see A here. And you have to choose two more, and you can choose any pair except for BC, which is exactly what it is here. Okay. So it just so happens that in this example, I started with a graph, with a graphical matroid, and I got a graphical matroid. That's not true in general. You might have hoped that it's true, that whenever you start with a graphical matroid, you got a graphical matroid. That would be nice, but it's not true. But I mean, you can imagine how many questions would come out of this. If I started with a linear matroid, is this one linear? If I started with a transversal matroid, is this transversal? If I started with a transversal one, is this graphical? I mean, there's so many things you could ask. And it'll take us some time to answer all of the obvious questions that come out of this. Okay? But this is, I think, one of the very, very nice basic things about matroids is that they have a duality. This guy is called the dual matroid. Okay. Is the dual of M. Now, maybe you've seen the word duality in mathematics before. And duality, whenever you see it in mathematics, has a property, which is what? That the dual of the dual is the thing you started with. Well, you know, if you start with the bases, and you take the complements, and then you take the complements of the complements, you get the bases. So the fact that complements are dual in a way gives you that matroids are, I mean, that this is really a notion of duality. In other words, you can call it a theorem, even though the proof is just theorem. The dual of the dual is the matroid that you started with. Proof QED. Just nothing to say there, right? You're just saying E minus B is B. Okay? There is something to say. Let's say it. E minus B is B. Period. Okay? So there's a theorem. And if you look at that theorem, it seems to be a theorem about bases. We only talk about bases. We started with a collection of bases. We ended with a collection of bases. Okay. But if I asked you to prove this theorem before telling you about circuits, I think you would find it quite tricky. But now we know something called circuits, and we're going to see that circuits are going to make this proof much easier. So proof of the theorem. Well, first let me give you a little. What's the strategy of the proof? We're going to prove that theorem in 3 steps. So the first step is that we're going to prove a lemma about circuits. Once we have proved that lemma about circuits, we will be ready to prove this other lemma about bases. And once we have this lemma about bases, we'll actually be able to to prove the theorem. Now you guys have all learned how to do mathematical proofs, and I'm sure you realize by now that if I show this to you in this order, then you're going to be able to follow it logically, but you're not going to understand where this lemma comes from. This is the way things are usually done in mathematics. You're trying to prove a theorem, and you say, oh, I need a property about bases. So let me try to prove this lemma about bases. And then you try to prove that lemma about bases, and you realize, oh, what I really need is a statement about circuits. And so then you figure out what the statement is that you need, you prove it, and then you pretend you were very slick, and you knew from the beginning what you knew. You knew from the beginning what you needed. Well, this is the statement that you need. Statement that you need is the following. It says, if I is independent and I union E is not independent, then that basically means that there's a circuit. Okay? Now, the way that I want to say this is that basically you had an independent set, and you added an element that made it a dependent set. Okay? So you found a dependence. And so the first thing I want to say is that there is a dependence. There is a, I mean, because this guy is dependent, there's certainly a circuit in there. Okay? But I want to put a word here. The idea being, and this motivation comes from vectors. In linear independence, if you have that I is independent and I union E is dependent, then that means that you can write vector E as a combination of the vectors in I. But not only that, you can write that in a unique way. Okay? And I want to show that this is also true for matrix. That not only do you have a dependence, but that dependence is unique. And of course, that dependence must involve the new element. So let me call it the unique circuit C. It must be in I union E, and it must involve the new element. My new element is in C. Okay? So hopefully this sounds plausible to you. You shouldn't know why this is going to help us prove the theorem, but we will see that. For now, let's prove this lemma 1. Okay? And maybe I'll advise you to leave a little space here in your notebook for something that I want to say that is about this long, 2 lines. Okay. Proof. Well, I union E is dependent, and everything dependent contains a circuit. Now, E better be in that circuit. Because if it's not, then C would be a subset of I, so it would be independent. So existence is pretty clear, but what I want to show is uniqueness. Okay, so let's suppose that I have another one. Another circuit D, which is in I union E, and I know that E must also be in that circuit. Okay. Well, this is exactly the setup for axiom C3 to apply. I have a circuit C, I have a circuit D, and they have an element in common E. So by axiom C3, I can find a circuit F contained in C union D minus E. Okay? But this guy, C union D, is a subset of I union E. So if I remove E from it, I got a subset of I. F is a subset of I. That's a contradiction because F is a circuit. So this guy is dependent. This guy is independent. Good?
Federico, what's the 3 mean there before they
Here?
Yeah.
So this is
Oh,
a C3. So what I'm using is the third circuit axiom. Okay. Any questions about this little lemma? So really the way to think about this is that matroid dependence behaves a little bit like linear algebra dependence. If you have an independent set and you add an element to it, and that element happens to be dependent, I mean that set happens to be dependent, then you can really think of it as E is dependent on I in a unique way. That's basically what this lemma is saying. Okay? And you use this often enough that this circuit has a name. So this is called, it's normally called C is called the fundamental circuit of E with respect to I. And there's actually a notation for this. People denote it by C of E, comma, I. Okay. So C is called the fundamental circuit of E with respect to I, and we denote it C of E, comma, I. Okay. And this is the circuit that you always want to use when you have an independent set and you make it dependent by adding one thing to it.
So there are I's. I is one of the independent sets in script I.
Right, so this applies whenever you have an independent set I, which becomes dependent when you add an element to it. Okay. So this is nice to know. And we're going to use that to prove a second lemma. And this time it's a lemma about bases. Let A and B be bases, and let B be an element of B minus A. Then there exists an element A in A minus B such that you can swap A and B. Take A, you get rid of little a, you add little b, and you get a basis. Now you might look at this and think, we know this already. Why is he going to prove it again? Because this very much looks like basis exchange. But what does basis exchange do? It says if you have A, B that are bases, and you have an element A in A minus B, then you can find a B in B minus A to swap it with. In other words, if you start with a basis, if you start with two bases, and you get rid of an element of the first one, you can switch it for an element of the second one. What this is saying is the opposite. It's saying if you start with two bases and you choose an element of the second basis that you want to add, then you can find an element of the first basis to swap it with.
That's a big A, yes?
This is a big A, yeah.
Right.
So this is almost basis exchange. It's just a little bit different. So this is a variation of basis exchange. And you might think that this is equivalent. I mean, that this is kind of a trivial thing, that if you have one, you have the other.
Is it not equivalent? I mean, could you replace the axiom with this? And
So there's two things you might think. One thing you might think is that I can just look up the proof of the real. This is called B2 star. So one thing you might think is that the proof of B2 and the proof of B2 star are identical. And that is not true. Okay. B2 star is harder to prove than B2.
it's a bit stronger statement, right? In a way.
It's not clear, actually, that it's stronger.
not
It's
clear.
different.
But it's saying that you can always add any B that's not in A, but it's in B. You can always add it. The other one was just saying you can find one.
I mean, the original basis exchange says if you have two bases, you can remove any element from this one
Yeah.
and fix that. This one says if you have two bases, you can add any element of this one and fix that.
Yeah.
These sound more or less equally difficult or equally easy, but we're going to see that this one takes a little bit more work to prove. Okay. And let me delay the answer to the second question. I'll address it. Okay. Well, I mean, I don't need to delay. The point is that this is equivalent to B2. So maybe I'll make this observation, which is not trivial. In fact, let me just say proposition and say this is not trivial. EB satisfies the basis axioms if and only if it satisfies the first basis axiom, which is, remember, B1 is trivial. It just says there is a basis. And B2 star. Proof. My plan was also to leave this as an exercise to you. Exercise. But I'm going to give you a hint, which is that actually you want to use duality. So to prove this theorem, really you want to use this one, which makes the point that this is not a trivial thing at all. Hint: use duality.
Wait. To prove what?
I'm confused.
What?
I mean, only because we're doing this in the process, in the service of proving this.
No.
Oh.
So this is a parenthesis. I mean,
Right.
To prove that
Oh,
proposition.
prove that proposition.
to prove this proposition,
Yeah.
you want to use duality.
Yeah.
Got it.
But this is a parenthesis because I don't need this. It's really because I wanted to answer James's questions. Is this an equivalent axiom? It is, but basically you want to use duality to prove that. Okay. So let's go ahead and prove this lemma 2. Where should I go? Let's see. Well, this theorem is easy enough to remember that I'll erase it. So proof of lemma 2. Okay, what am I going to say? I'm going to say, now you can imagine that I want to use lemma 1 And Lemma 1 was saying what happens when you take an independent set and you make it dependent by adding an element to it. Well, you can kind of see the situation happening here, that A is independent because it's a basis. But if I add this element B that I'm supposed to add, then it's already a basis, so this must create a dependence. Okay.
Wait, so are you essentially proving one of the directions of that proposition? Is that what's going to happen here?
Right, so basically, what I'm proving right now is this direction.
Yeah.
That the normal basis axioms imply this modified basis axiom.
Sure.
And I'm not going to prove the other direction. I'm leaving that to you. Yep?
I'm just a little bit confused too, because it is lemma 2 and then you have proposition, and I thought they were two different things, that that's, the proposition is all part of lemma 2 and then we're proving that now, or confused about what we're proving.
So maybe what you should think is that this is not here at all. You didn't see this. It's not.
So we are proving lemma 2 and the A is the A is the element of B in the top.
Right. So maybe I'll come back to this, but for now, forget that I wrote this at all. And I'm just proving this statement about, and it's just a statement about bases in a matrix. So it's okay. I have two bases, A and B. I want to add element little b to A. I want to find an A to swap it. So what I want to do is say, well, I had my basis A. I added the element B to it. So I created a dependence. And now I need to fix that in some way. So A was my independent set. I created a dependence. Okay. And so the point is that the only real dependence, there's basically a unique dependence in here, which is the fundamental circuit. So the only real dependence here in A union B is this fundamental circuit of B with respect to A. Okay. So when is this guy a basis? This guy, A union B is dependent. Now I want to make it independent by removing an element little a. How can I do that? Well, basically what I need to do is break this dependence. Okay. A union B is has a dependence, it's this one. So if I want to get rid of that dependence, what I have to do is break it. In other words, the element A that I'm removing has to be one of these elements involved in the unique dependence in here. It has to be one of the guys in the fundamental circuit, and of course it can't be B. A is not equal to B because B comes from the other basis. Little b, by definition, is not in A. Now, this is the idea, and I mean, is it clear to you guys that this is the idea? I had an A union B which has a unique dependence, it's C. So if I want to make it into a basis, all I have to do is break that dependence. Okay. There is a detail to be filled in here, and it's very easy, and you should do it yourselves, but this is basically the argument. Okay. So if I want to find a basis, then all I have to do is find an element that is in C. So all I need is an element which is in C, and it's supposed to be in A minus B. But why does that element exist? It exists because C is dependent and B is not dependent. So C cannot be a subset of B. And if C is not a subset of B, then that means you can find an element A which is in C and not in B. Okay. Any questions about that?
I'm just not seeing the third line of how A minus A union B is the basis.
So you're not seeing this statement right here. Right? Is that the one?
Yeah, I mean, we know that A union B is not independent, but A minus A union B. So A is coming from the circuit.
So I mean,
But A is an A to begin with.
maybe let me go ahead.
So what I was going to say is that I think what that sentence is saying is that we want that A minus A union B is a basis. And that, so what we want is that first part. And what we're saying is that's equivalent to finding some A and C that breaks this. So he's just saying going after this thing being a basis is the same as going after an A and C that will do this for us. And then he says, so now how do we find that? Look at the
Right. I mean, I think the reason you're not seeing it right away is because, I mean, I did say here, there's a detail, right? What I'm telling you here is the intuition, right? I'm telling you the only real dependence is C, and so what you have to do is break the dependence. Now, that statement, you have to prove it, and it's very easy, okay? But there is something to be said here. And actually, we're out of time, and so I don't have time to prove it for you, but in fact what we'll do is I'm just going to post this in the forum, and we'll talk about why exactly this is true. What I want you to understand is that this is pretty clear for linear matroids, for linear independence. Okay? So think about why it's true for linear independence, and think about why you can generalize that to any matroid. Okay? But for now, let me stop here saying that as soon as you understand why this is true, we have proved lemma 2. And next time I'll start by proving the theorem about duality. Okay? And if for some reason I forget to post this question on the forum, then someone else please do it for me. I think I'll remember. But
Federico,
this one here, when we're supposed to prove that they're non-isomorphic, that means that no two of them are isomorphic?
that's right.